finish up this particular chapter, atmospheric pollution and its dispersion. So let me share my screen. Okay. So last class, let me just adjust. Okay, so last class we were investigating motion of the buoyant plume. So we have considered this particular simplified geometry where we have a stack of height hs, and we define the coordinate system somewhere on the top of the stack xp and zp, and based on that we try to find out how the buoyant plume trajectory will happen as you move away from the stack in the horizontal direction, and what will be its effective height when you go high. So that is effective height will be h. So we have found that we can actually define a buoyancy length scale, which is a relationship between uh, this buoyance force per unit time per unit effluent density or stack density divided by your velocity of the wind, cube of that. So from that you can define a length of or buoyancy length scale, and using that you can find out actually what will be your like the trajectory of the plume as you are moving away from the stack, which can be written as xp as you're moving away, x direction coordinate, and zp will be your vertical coordinate. So without going into the detail of the derivation, that momentum equation and all, we just saw the final results. Okay, so these are the final results that relates your zp and xp with this one buoyancy length scale. Okay, and we also try to correlate your natural frequency of oscillation of air pollutant. So that is only possible to do when you are considering the atmosphere is a stable condition or is under equilibrium. Okay, so that relation is shown here. You can relate the vertical height um, dispersion of the plume along the vertical direction, that is zp infinity, like infinity will be at a distance where it attains the equilibrium, okay, at a height where it attains the equilibrium, and that can be related with your wind speed, buoyancy length scale, and natural frequency of oscillation of the air pollutant. Okay, so that formula is also given here, n is equals to this much.
Excuse me,
Yes.
sir, like once the like that set of pollutants attains a attains an equilibrium, can it become unstable again?
Okay, yes, definitely it will be like I'll say it will not be unstable. It will try to settle down afterwards, because as it is staying in the upper atmosphere, it is also reducing its velocity, like the velocity with what it has been released. It is also slowing down subsequently, and also it is mixing with the surrounding. That's why what is going to happen, it will not go high anymore, like it is going to stay in that particular equilibrium height for certain time. Afterwards, when it loses its velocity more, it is going to fall down. Okay, so we will see that there is another formula which is derived by another scientist subsequently, like what is the plume rise
Uh,
height.
uh, okay, sir, is it like this that when the like surroundings will come to an other equilibrium state, then it will try to settle to that equilibrium?
Yes, it is a
Uh,
dynamic process. Like if the surrounding suddenly changes, which is unexpected, like if the surrounding condition is changing drastically, then the equilibrium may not be possible. Okay, so it depends on several factors. Like basically, you can see what governs the plume rise. It's a buoyancy force. So how the buoyancy force is or can be modified depending on the temperature of the this stack material, then the temperature of the surrounding. Okay, and also the wind condition. So these three things, if you can find out a suitable equilibrium by if there is a possible force balance, then it attains equilibrium. If not, then there will be either unstable situation or a neutral condition. Okay.
Okay.
Okay. So yeah. So in general, what you see here, this is a schematic of the plume condition. Like this is your stack height h, and delta h is your plume rise, which is previously I said ZP infinity. Okay, so the same thing. Don't get confused. So delta h is your plume rise height. Okay, and h is your effective height. Okay, so which is h plus delta h basically. Now, if you see the plume, generally they are fluctuating. There will be some scale of fluctuation. So instant on an instantaneous trajectory, you can see that that may look like there's some sort of fluctuation. Okay, but if you do a time averaging of that, you can very well find out they follow a particular type of density distribution or probability density distribution function. So this is something similar to a Gaussian distribution. Okay. Now, so if we define the coordinate system x along this direction, z is vertical. So you can see that along the vertical direction, the concentration follows uh, the time average concentration. Basically, it follows a Gaussian type of distribution. The same thing happen if you are considering about the y direction also. So y direction will be perpendicular to the screen. So y direction also, you can see that there will be a Gaussian distribution. I have a figure subsequently, I think. Let me show the figure. Yes. So you can see that z direction, it follows a Gaussian type, and also along the y direction it follows a Gaussian type, and x direction is dominated by the wind itself. So there is no particular pattern. So this is just advection. Okay. So if you want to find out the concentration of the plume or the pollutant in this case, so that you can obtain by, if you know the probability density distribution function, or you can define this Gaussian distribution function appropriately at a different location, like at this location or wherever is your interest. So if you can find out the density distribution function at that location, then you can get the concentration appropriately. So this is actually a empirical model. It is not the actual solution, because you can see that the actual solution is quite difficult to obtain, because there are several processes you need to include. One is your turbulent flow mixing. Sorry, turbulent flow scenarios. What is the turbulence level in the wind itself? Then the mixing process. Okay, so when the pollutant is released to the atmosphere, it may be mixed among themselves. That will be like the temperature gradient. Then the chemical interaction. Okay, so whether they're chemically reacting with the surrounding, and different type of time scales also you need to take into account, because the dissipation rate is not same for all the pollutant or the material. So all these things will take a lot of computational effort, and sometimes it is not also accurate to predict. Okay, so rather doing such a large scale computation, it is found that the Gaussian plume model or Gaussian model for the Gaussian probability distribution function approximation for the plume concentration is quite valid. Okay, so that's why you can use this simplified empirical method instead of doing the full scale computational simulation. So, but when you are using this or such type of empirical method, basically you need to have certain simplification, or in this case certain assumption you need to make. So these are some of the assumptions that should be I mean, you should know before you apply the Gaussian plume method. So your pollutant, release of the pollutant is considered as a point source. It's a point source and it is continuously emanating the pollutant. So it's a virtual point source. Then advection is only done by the wind. Okay, so wind is or atmospheric condition is only doing the advection of the pollutant. Then similarly, the dispersion of the pollutant, which happens along the z and y direction, okay, and that spread follows a Gaussian type of distribution. Okay, so that is another assumption. Then there is a constant rate of emission of the pollutant. Okay, from this point, so there is a constant rate of emission, and this one is you can understand that this generally the chimneys or stack, they are placed inside the boundary layer. Okay, so but in the boundary layer velocity profile continues to evolve. Okay, but in this particular plume model, we assume that the wind speed remains constant at a with time and the elevation. That wind speed doesn't change with the elevation. Okay, so this is another very much simplified version. You can see that this is not correct, but the amount of change in the wind speed may not be very significant. That's why it is still okay to as have this assumption. Then another thing is pollutant is conservative. That means non-reactive among themselves. Okay. Then pollutant is reflected by the ground. It is not absorbed by the ground. It is reflected. Nothing gets absorbed by the ground. Then open terrain condition is valid. Like we do this simplified this plume model, or this plume model is established for a flat kind of terrain. Okay. Then another thing is the atmospheric stability is uniform. The stability doesn't change significantly during short span. So stability is uniform. Okay. So these are some of the assumptions which make the model very simple, and but it is found that it is quite applicable to find out the concentration level. It is not that bad, but it is quite good also. So with the very first thing, okay, already we have discussed the nomenclature. H is your effective height, and the small h is your stack height. The remaining part is delta h, which is your plume rise height. Okay, so this plume rise height, yesterday we have related with the buoyancy length scale. So yeah, before I go to there is another formula for it, but here why the plume doesn't continue to rise, because there are few factors, because they mix with the surrounding air, they lose velocity, the initial velocity with which they are released, that velocity subsequently is lost because of the viscous dissipation, and also they cool down by the mixing among themselves. So because of this thing, the density of the pollutant is increased and they cannot go high. Okay, so after certain height, they starts to fall down or settle down. Okay, so here this delta H, we have seen one of the formula that relates the buoyancy length scale, but there is this formula is more used when we define delta H, given by Holland's. So Holland's formula, here you can see that Vs is your stack exit velocity, that exit from the chimney, and D is your stack diameter, that exit diameter. U is your wind speed at that particular height. Okay, and remaining thing is your D is already defined. P is your pressure, atmospheric pressure condition, and that is you have to be careful while you are using the values in this formula. So because you can see that there are few numbers here, so if you don't use proper units, you will end up in a wrong result. So P you need to define in millibar. Okay, so this is atmospheric pressure. TA is your stack gas temperature, defined in degree Kelvin, and TA is your atmospheric temperature, again defined in degree Kelvin. Okay, so these three things I think you need to be careful: pressure in millibar and temperatures in degree Kelvin. Okay, so based on that, other things I think quite straightforward. You can find out delta H. This is your plume rise height. So once you know delta H, uh, sorry, this is small. So the formula is with small h, so don't get confused. So delta H and this physical stack height, once you add them together, you can find out effective height. All right. So that effective height we are going to use to define the Gaussian concentration, plume concentration. So this is the formula for the Gaussian plume concentration at any location x, y, z, sorry, x, y, h. Okay, so here basically I think the nomenclatures you can see here. This is kappa. So that one is your downwind concentration at the ground level. Okay, so this downwind concentration at the ground level, which is the unit is gram per meter cube. Okay, and E is your emission rate of the pollutant, which is gram per second. SY, SZ, generally these are standard deviation, which are also defined as sigma Y and sigma Z. So basically these are standard deviation for the Y and Z direction. Okay, because um, like we have seen here, basically the plume shape become Gaussian type along the Y and Z direction. So you will have two different standard deviation for the Y direction one and for the Z direction one, but for the X direction you basically don't need any standard deviation, right? So this is SY and SZ, and U is your mean wind speed, and these are the distance. Okay, so yes, now this is the formula, pretty straightforward to find out the concentration level at any height and at any distance x. So once we do a numerical on this, it will be clearer how you are going to actually find out the concentration. So I have a numerical subsequently. So in this formula, what you can see is this will be generally known to you. Wind speed will be known to you. Okay, and sigma y, sy and sz, the standard deviation part you need to find out based on the atmospheric stability condition. So there will be few plots we will see subsequently. So from that plot you need to find out sy and sz. Okay, and h is your effective stack height, that is generally given to you, like or if it is not given, then you need to find out using the Holland formula. Okay, so first you need to find out the plume rise, then so that is delta H, plume rise using the Holland formula. Then H is your physical this chimney height. So H plus delta H, then you can find out what will be your effective height. Okay, so if that is not given, you need to find out the way I explained. Then Y and X are those generally are the variables, the desired location where you are trying to find out the concentration. Okay, so remaining thing is, I think there is no other variables. Okay, now I said you need to use the atmospheric stability condition to find out sigma y, or sorry, sy and sz, which is your standard deviation part of the concentration. Okay, so that depends on the stability of the surrounding or the atmosphere, which is quite obvious. If the atmosphere is having a different stability condition, the spread will be different. So that's why the probability of finding the pollutant changes, or that means the standard deviation part is also getting modified. Okay, so
Excuse me, sir.
here, yes.
Sir, like in the previous slide, here, uh, like we can't vary the Z.
You know, jet cannot be varied. So this formula is for this one effective when you are reaching a equilibrium condition. So that's where you define your effective height. So
Okay.
plume rise is fixed term. You can see that this is a fixed value. It cannot be changed. Okay, for a set of parameters, whatever is the release temperature, whatever is the wind speed, based on that you will get a fixed delta H. Okay, so that's why
Okay,
H becomes fixed afterwards.
okay,
So, but the concentration will vary as you are moving along the X and Y direction. So this is X direction, Y is along this side. So at a particular Z level, which is your effective height level, you can see that this concentration along the Y and X gets modified. Okay, which is of our interest, like how it is getting modified as you are moving away from the stack along the along the horizontal plane, basically. Okay, that spread is more
okay,
important. All
okay,
right. So these are the stability criteria that you need to follow for determining the SY and SZ. Okay, which are your standard deviation parameters. Excuse me. So you can see that in this table, basically, wind speed is one of the factor that defines the stability condition. The second factor is your solar radiation received during the daytime and during the night time. Obviously, you can see that these two will be the parameters which can define the stability condition of the atmosphere. So if the wind speed, so these wind speeds are defined at a height of 10 meter from the ground level, and the wind speeds are in meter per second. Okay, so this will be, you can consider as the reference wind speed because it is generally it is measured in any of the weather stations. So wind speed at a height of 10 meter defined in meter per second during different time of the day. So if it is during daytime, if the solar radiation received is very strong, moderate, or slight, based on that you can define your stability parameter as A, B, C, D. So here A, B, C, D up to F it is mentioned here. A is being extremely unstable, B moderately unstable, and this follows. D is a neutral condition, E is slightly stable, and F is moderately stable. Okay, so during the daytime you can see that at certain duration the atmosphere is extremely unstable, and certain time it is unstable, and few duration it is neutral. So based on the wind speed and the solar radiation received, like Arsajit, you were asking yesterday, right? What time we release the plume, and what will be the best condition to get the um,
yes,
means what shape it follows. So generally, if you can release during this stable condition, that will be well and good. But it is sometime unavoidable because your factory needs to run, or the production may happen at any time of the day. So based on that, they might end up in various situations or circumstances that then the plume profile will follow accordingly. Okay, but they keep in mind generally try to release the plume during the stable situation like E or F. Okay, um, let's not go into that part because that is not I mean, we are not going to get any quantitative information from that discussion. So rather here what I'm going to tell you is so how to use the Gaussian plume and find out the concentration for the Gaussian plume model. Okay, so first thing is in this formula you need to find out this SY and SZ, and SY and SZ depends on the atmospheric stability condition. Like you have seen in this table, it depends on the date, what time of the day the plume is released, and what is the wind velocity during that condition. So based on that, there are these plots are already done experimentally, and these are obtained already experimentally. So A, B, C, D, E, F, like those are the atmospheric stability criteria just now we have seen. And for the horizontal dispersion coefficient, that is SY, and the distance from the stack or the chimney. Okay, so along the x-axis you can see that this is the distance from the chimney, And along the y-axis, you can see this is your standard deviation part, and there are few lines you can see. Okay, so uh, based on the condition what you have obtained, like let's say you are falling in this B category, okay, based on your wind speed and the solar radiation received. If it is falling in the B category, then you have to find out at what location is your interest, like from what location you are trying to find out the pollutant concentration along the X direction. Go to that particular, let's say here we are thinking about 2 kilometers. Okay, so go to that, and after that you can find out SY, your standard deviation, corresponding to that particular line B. Okay, since we found that B is the atmospheric stability at that particular duration, so from there you can find out what will be the corresponding SY. Okay, so you need to follow. I think this is pretty simple. It is not very difficult. So that height, what will be your SY, you need to find out on that particular line B, C, A, depending on the atmospheric stability condition. Okay. Similarly, there are also another plot which you can find out for the vertical dispersion coefficient, or SZ. So it's similar to the previous one, but this is for the vertical dispersion coefficient. So using this plot, these two plots you can find out SY and SZ. So once SY SZ is known, so SY SZ is known, wind speed is generally known, and E is the emission rate is known, then you can find out the concentration at desired X and Y. Okay. Another thing is, sometimes the wind speed information you generally get at the reference location, like 10 meters height or so. Okay, but you may need to, so in that formula, concentration formula, you need to use the wind speed information at the effective height, that means at H. Okay, so for that, what you need to do is you need to use this power law model that we have seen in the previous chapter. So this is the power law model, and you can get this index here, P, and that varies also depending on the surface roughness condition what we have what we have seen previously, and based on the stability condition also, atmospheric stability condition, if it is ABC, like just now we have defined the stability conditions. So based on that, this suitable P value can be taken, and once you know the P value, you can find out what will be your wind speed at the effective stack height. So U1 can be your reference wind speed. Based on that, since you'll be knowing Z1 and Z2. Z1 may be your reference height, which is 10 meter. Z2, you can think about it is your effective stack height, okay, which is your capital H. So from that you can find out, from using this formula, you can find out what will be the wind velocity at the effective stack height. So this you need to use in the Gaussian plume method, this velocity, okay, if it is not given to you. Okay, so let's do two examples. I think that it will be pretty much clearer. So the first one is estimate the plume rise for a 3-meter diameter stack whose exit gas has a velocity of 20 meter per second when the wind velocity is 2 meter per second. Okay, so you can see that this is your exit gas velocity, wind velocity is 2 meter per second. Okay, and the pressure is 1 atmosphere, and the stack and the surrounding temperatures are 100 degrees Celsius and 15 degrees Celsius. So basically you need to find out plume rise height. Okay, for that what you need to do is you need to use this Holland formula. Okay, so here all the informations are already there. Vs is your stack velocity, which is your 20 meter per second. D is your diameter of the stack, okay, which is your 3 meter, already mentioned here. Excuse me. And this U is your velocity of the wind, okay, wind velocity, which is your 2 meter per second. The other thing what I have said, you need to be very careful about the units of pressure and the temperature. So pressure you need to mention in millibar, which is this 1 atmosphere. If you convert it into millibar, will be this much. And TS is your stack temperature, 100 degrees Celsius. Convert that to degree Kelvin. And TA is atmospheric temperature. Convert that to degree Kelvin. Okay, so from that you can find out what will be your plume rise height. Okay, 101 meter in this case. Okay, so I think it is clear, right? It is not very difficult to follow. So the next question is, this is on the Gaussian plume model. A stack in an urban area is emanating at a rate of 80 grams per second of nitrous oxide. Okay, so it has an effective stack height of 100 meter. This is, you can see that effective stack height is already given to you. Okay, so you don't have to use the Holland's formula anymore. This is your H. Okay, the wind speed is 4 meter per second at 10 meter. Okay, so this at 10 meter height, your wind speed is 4 meter per second, but the wind speed is not known at height of 100 meter. So it is a clear summer day with the sun nearly overhead. Okay, so you can see that the sun condition is somewhat in the noon time, right? So it's the strongest in the day. So the condition you need to find out atmospheric stability for this. So this is the strongest solar radiation received during that time. Estimate the ground level concentration at 2 kilometers downwind on the central line and 2 kilometers downwind, 0.1 kilometer off the central line. Okay, so there are two information you want to find out: one along the central line, one along the means off the central line by this much of amount. Okay, so how do you do it? So the very first thing you need to find out what is the atmospheric stability condition for the wind velocity and the solar radiation received. So you can see that the wind velocity, it is mentioned that at a reference height of 10 meter, it is 4 meter per second. Okay, so on the first column, you need to find out where it is coming. Okay, so it will be in this range. Okay, 3 to 5, right? 4 is here. Now the solar radiation received. So it is said that the solar radiation, it's a summer day. It's a summer day. Then the sun is also nearly overhead. Okay, so it's a noon time. So that means it will be the strongest. Okay, so you can see that atmospheric stability condition will be B. Okay, 4 meter per second, and this will be B. It's clear. So based on the information available to you, you can see that the other atmospheric stability parameters can be also achieved. Okay, so for this particular problem, it is B. Now what you need to do is, the next thing is, there is another information is not known. What is the wind speed at the stack height? Here the stack height is 100 meter, right? But the wind speed is only given or known at 10 meter height. So we need to find out wind speed at 100 meter. So how do we do that? Using the power law model. So that just now I have discussed. So in this case, you need to find out the suitable index. So P in this case, like we know the stability condition is B and it's an urban condition. So you get 0.15. Okay, so you just need to substitute 0.15 here, and from that you can find out what will be the wind speed at a stack height. It is, or effective height, it is 5.65 meter per second. Okay, so using this power law model, you can find out what will be the velocity at the effective height. Yes, so here it is mentioned that you don't have to use the Holland formula because already your effective stack height is known to you. Okay. Now next thing is, you need to find out the standard deviation parameters along the y and z direction. Okay, so what are the location what we are interested at? It is 2 kilometers downwind. So x distance will be 2 kilometers, and for both the case, right? This is 2 kilometers downwind. Okay, so 2 kilometers if you take in this particular plot. Okay, so this plot is not clear, but the values already are mentioned here. Okay, so 2 kilometers you need to go, and on the line B, because B is your atmospheric stability condition, and you will find out sigma y is your 290. Similarly, this is along the horizontal direction because sigma y you are trying to find out. Similarly, on the vertical dispersion, sigma z, you can find out again 2 kilometers, and on the line B, it will be 220. Okay. So these two values are what you are going to obtain from the plots.
Sir,
Yes.
like the zero level, here is the stack height or
Zero level,
the ground level.
if it from the ground level, from the ground here, the coordinates are from the ground. Okay, I think that is what yeah, you can see this is from the ground level. Okay, x, y, and z, this is the origin here. Okay,
Oh,
so what we have discussed yesterday was from the top of the stack, but for the Plume model, it is from the ground itself. The ground is 0. Okay. So here you can find out Sy and Sj. All right. So now I think everything is known to us. So if you see the formula, let me just quickly go back. So going back and forth is not okay. So E is your emission rate, which is known to us. Sy, Sz, we just now derived. U is your wind speed and the effective stack height. We also obtained that. Y and H. Y and H. H is your effective stack height. It's already given to us 100 meter. Y is your, this is the offset parameter, right? This offset value for one particular case it is along the center line, for other case it is away from the center line by some distance. So accordingly you need to choose the y value. X value you don't have to worry about because based on the x value only you are defining your sy and sz. Okay, so that is the location where you are defining the standard deviation part for the concentration. Okay, so if you go to that formula, so just substitute the values here, 80, and this is your SYSZ, and this is your wind speed. That is what we just now obtained. And for the center line case, this is Y will be 0, and effective stack height is 100 already given to you. Okay, so just substitute, and you can find out what will be the concentration at a distance of 2 kilometers or 2000 meters along the center line of the the stack. Okay, so this is along the center line. If you see this plot, so basically along this center line, okay, the dotted line is your center line. Okay, the other case is offset by certain distance. If this is your positive direction here, we consider, then by 0.1 kilometer offset, what will be your concentration? So that you need to find out. I think the same information will be applicable. X and Y, just you need to substitute the y value here. Okay, so in terms of meter, so in this time to convert it into meter, and the remaining values will be same because your x location is same. Okay, so your remaining sy, sz, all those values will be same, and you can find out the concentration here. Okay, so which is 60.6 microgram per meter cube. The previous case it was 64.3 microgram per meter cube. Okay, so at the center it is expected that will be higher because your peak will be at the center line, and away from the center line it is obviously expected to be reduced by some value. Okay, so I think this is where we will stop for atmospheric pollution dispersion. So we have considered only a point source of the emission of the pollutant. There could be a line source, or there are few more analysis which I think it's not necessary. Considering only point source is good enough. But in some cases you can find out this point source emission may not be very applicable. You should be knowing that what are the limitation of this particular Gaussian plume model. There are few other techniques or few empirical models are already proposed which improve upon this Gaussian plume definition of the plume model. Okay, so those I think it's not necessary to discuss in this particular course. Okay, so I stop here. Please try to go through the numericals again. If you have any problems, you can get back to me. All right. So any question? Okay, if no question, we stop here today. We will meet again Wednesday. Okay, next week Wednesday with the next class. Okay then, have a nice weekend.
Thank you, sir.
Bye bye.